Okay, HiMake started life in 2002. It replaced template-based recursive make build system. It had this problem that build took forever. But actually the main problem with it was that all the build intelligence or build knowledge was distributed into hundreds of makefiles. So HiMake is a second-order build system. It generates makefiles from simple build description files, and then it offloads the actual build to make. And in that regard, I think it's similar to CMake and QMake. But we also think HiMake has some features that some of the other build systems don't. In our organization, we try to build from source as much as possible. We think it gives quite a lot of flexibility and high dynamics in the development process, because anyone can change code everywhere, and whether it's changing an API or inserting a printf for some debugging. Also, it has this advantage by building everything with the same compiler and the same compiler switches. We avoid application binary interface problems, and we also avoid one definition rule violations. Of course, there are some exceptions to this. For instance, Qt and Boost, which are really big binaries or libraries, they are provided as precompiled libraries. Okay, design principles. HiMake was designed to be easy to use, and that also implies it should be easy to use correctly. One of the things it does is it puts all the build intelligence into one place. HiMake is also cross-platform. It cares about correctness. It cares about fast builds, and it also has quite a lot of flexibility. When that said, we also think that HiMake is an enterprise build system. It's not something you use to build trivial applications. Everything is controlled and deterministic. There's nothing like, we need a C++ compiler. Let's try to find one on the system. Or we need Boost. Where is Boost on this computer? Either Boost is there or it's not there. You never go searching for it. That also means that when we do a build with GCC 8.3, that will be different from a build with GCC 7.2. And the same if it compile with C++ standard 11, that will be different from a build with standard 14 or something. HiMake has always supported multiple tools and multiple platforms. When we started this in 2002, we compiled on HP UX with the ACC compiler and Solaris and GCC, and we cross-compiled to the PSOS operating system. A little bit later, we got support for Visual C++ on Windows. And then we moved on to Linux, and we supported GCC on that. And we started cross-compile to VxWorks. And the current status is that we do most of above, but we also cross-compile to the Integrity OS with the multi-compiler. And we support quite a few embedded Linuxes with their tool chains. HiMake has a lot of features, and I'm going to give you a list, but I'm not going to talk much about them, just to give you an overview. Okay, we can do out-of-source builds and in-source builds. We generate makefiles for GNU-make and for ClearMake, which is part of ClearCase. We can do parallel builds, distributed builds. We have support for Unity, or what some people call the jumbo build support. We can generate project files for a static code analysis tool from Perforce. Can generate a JSON compilation database, which, for instance, ClangTidy uses. We generate static libraries by default, but can also generate shared objects or DLLs. Qt plugins, MATLAB executables. We generate all our documentation through HiMake. Has support for many languages and tools. assembler, C and C++. They are kind of the more common ones. Then we have the Corba IDL, Lex and yacc, the Qt toolchain. And we have quite a few kind of internal special purpose code generators. We can enable the sanitizers that are part of Clang and GCC. We can instrument the code with code coverage. For a code coverage analysis tool, SquishCodeCo in our case. We can track and report third-party licenses, export regulations, security classifications. That's an issue in our business. And it has a plugin that goes into the Qt Creator IDE. But I'm not going to talk much about these features. I'm going to talk about other things. One of the things is we think that HiMake is really simple to use. And I said that was the design goal. So HiMake has these build description files. They have this suffix HMK and the general name pkg.hmk, which is unpronounceable. So we call them HiMake files. And there's one HiMake file for each directory. And you have this term that a directory with a HiMake file is a package. So most of the time we just talk about packages. Okay. The HiMake file, it uses a declarative language to describe the source files to build, the executables to create, and dependencies to other packages. So if you look at the first one here, the first example, that one creates a library. And you can see there are two keywords in the beginning. Both of them are, actually all keywords are prefixed with HMK. That makes it easy to do error checking. So if the user makes a kind of stupid typo, HiMake will catch that and give an usable error message. Well, the first one, it specifies, okay, this library is going to be built from one C++ file called myutility. Then it has, this library has one header file that is going to be exported or made available to other packages. Then this package depends on two other packages. So you can see I've written it depends on the header-only library from Boost. And it depends on some basic types from some component. All other identifiers you want to use, you can use. They are just temporary variables. You can use conditionals. I haven't showed that, but you can do that. Come on. The other example shows how to create one executable. So you state, okay, there's one program, it's called exe. Then you associate one C++ file with that executable, that's the second line. And then finally you say, okay, this executable needs this package compar adapter in order to link. So one goal of HiMake is that the HiMake files are very precise. There are absolutely no redundancy in them. And we think there are no unnecessary declarations either. We don't specify paths to include files. And we don't specify the name of the library to produce or the libraries we use. So quite easy. Just to give you an example of how we can build, let's assume we're going to build for Red Hat Enterprise Linux 7.2. So the command line is going to be something like this. First, the name of the executable, then we specify the name of the HiMake file that describes the product or the executable. And then we specify the platform. So in this case, it's a platform that defines how to build for Red Hat 7.2, 64-bit. If we were to build exact same thing for Windows, we would just replace the platform. That's it. So there's another platform that specifies how to build for Windows 7 with Visual Studio 2015, 32-bit. And finally, I have an example that if we were going to build the same thing for our embedded computer that runs Integrity 11, it would be like that. Just a third platform. So the platform is a high-level abstraction of what to build on. That's what we call a build architecture. What to build for, that is a runtime architecture, and how to build. And that is the compiler type, whether it's GCC or Clang or whatever, and the compiler version, the compiler flags, linker flags, and so on. Everything is kind of abstracted into this platform. And the platform is part of one of many, many configuration files. So we have a tool specialist that maintains these centrally controlled configuration files. So the platform itself just specifies a default configuration, and then we have many canned or ready-to-use build parameter variants. So if you take an example for the Red Hat Enterprise Linux, we can choose between 4 optimization levels, like release, debug, non-optimized, and so on. We can select between 5 versions of GCC and Clang, 4 level of compiler warning strictnesses, default strict, and it ends up with pedantic, 4 C++ standards, and so on and so on. And actually, this comes to a ridiculously large number of permutations. So, but most of them don't make sense. I think in practice, less than 100 permutations are ever used for Red Hat. But then, okay, this was Red Hat. Then we have the same platforms, and we have these variants for PSOS, VxWorks, Integrity, Windows, and so on. Okay, in regard to HiMake, we have some vocabulary or terms. So I already said we have this package, which is a directory with a HiMake file. Most often, a package produces a library or an executable. Then we have a package set that organizes one or more packages. And these packages are referenced by text identifiers. You saw that before, but here comes a more good explanation. So these identifiers consist of a package set ID, say compfu, and that is system unique. So we have a kind of a librarian that allocates these. And then we have a package ID, in this, for instance, adapter. That one is just unique within the package set. And together they will form a fully qualified package ID, compfu/adapter. This makes it easy to move code around. We move the code, and then the librarian just changes the path to the package set. And these identifiers are also used for a number of other things, like creating the name of the library, targets in Make. Okay, so these identifiers map to paths. So the package set ID maps to an absolute path. So the compfu could map to workspace components foo, and the package ID will be a path relative to the package set. So in this adapter/source, for instance. And that means whenever we see in a HiMake file a fully qualified ID, like compfu/adapter, that can be mapped into an absolute path, a full path. In HiMake, the packages shall specify the direct dependencies to other packages required by the source files. It should never specify any transitive dependencies. And together, these packages or dependencies will form a directed acyclic graph, a DAG. And this is a simple DAG of packages. It has a root at the top. That one is generated by HiMake always. Then it's an executable, number 1, which again depends on 2 packages, A1 and A2, which it again depends and depends and depends. If we were going to build another executable, we can just kind of add it into the same DAG. You can see it has most of the common, the same packages as common dependencies as before. It's just a new executable. So this is looks kind of easy. And I just want to say one thing. The DAG we got here on the left is a DAG of packages. Sometimes when you talk about make, you're talking about DAG of source files and object files. That's what I got here in the right corner. So within each of these packages, there will be a DAG like that. But in HiMake, you don't really care about that. Yes?
Is it possible to put a library and an executable in the same directory, in the same HiMake package?
No. A package cannot produce an executable and a library. No. But it can one package can produce more than one executable, but not both, not both types. A DAG in the real world will look more like this. And HiMake will verify that there are no cycles in this graph. It is a DAG, so we must ensure that it is a DAG, acyclic. Okay, we have these keywords. They specify the task. So the users use the keywords to specify what source file do I have. And each keyword has an associated task that describes how shall the source file be processed. And there are some simple tasks like this. Just the C++ file. The C++ file will be compiled into an object file, will be put into the library, and finally will put into the executable. And here's another one. We call it a static CC sources. We use it for our test files, for instance, used by gtest, Google test. One case with them, they should not be put into a library, so they go directly to the linker. Also, we have more complex tasks, like this is an IDL, Corba IDL3 source file. You can see it goes through all this chain of tools. First, the IDL compiler, which generates an ACL file, and the C++ and two header files, which then goes through the ACL compiler, and you can just follow it on. But the thing is, the user or the developer, he just specifies this IDL3 sources. HiMake takes care of everything else. So the tasks, like the IDL task, is chained to the ACL task, which again is chained to the CC. So it just kind of passes on the files to the next task in the chain. Okay, you got the HiMake file like this, two source files and some dependencies. And then how do you actually find the dependencies? Because getting a list of files, that's easy. This can be difficult. Okay, the observation is that dependencies are most often governed by the hash includes. So you can assume that one of these C++ files do this include. So the question is, which package provides this header? So what HiMake has got is something we call the Dependency Finder. It creates an index by scanning for header files in all packages, in all package sets in the workspace. And then it makes a map from the header file to the fully qualified package ID. So we end up with a file like this. But this dependency finder also knows that from an IDL file, there will actually be a .h file. So if you look at line number 3 and number 4 there, you can see there's the IDL file. That's an actual source file. The line number 4, that's a generated header file. And then the dependency finder goes on to scan all the source files in this package for hash includes. And then it's a simple job of just looking up into this index and generating the set of dependencies. Yeah, build correctness. HiMake has some features for that. One thing, we try to catch possible one definition rule violations. Because if there are two packages that export the same header file, and they have the same name, but different contents, that could, in the worst case, be two different versions of the same class. And if some C++ files are compiled with the first header file and some are compiled with the second header file, we will probably get the one definition rule violation, and that is undefined behavior. So what HiMake does is that since it knows everything about all files, it will just check, are there any two files of the same name exported? It makes that assumption that, okay, if the names are identical, we will just give an error message. And then we have the case of, have you ever renamed a header file in the version control system, but continued having a CPP file referencing the old name? Or have you ever had an executable but changed the name of the executable, but still continued testing the old one? And you didn't find out until you cleaned the workspace? And well, there's a build system called TUP. And there's a reference at the bottom there. That gave me an idea to implement this feature, how to delete stale derived objects. So actually, I think the left example there, here the HiMake file used to specify mycomp.cpp and mycomp.h, and then they changed the names of the files. And then on the other one, they changed the name of the executable from foo to bar. So what HiMake does is, when it creates the make files, it will also create an index of mappings from source file to derived objects, and from derived objects to derived objects. And it's going to look something like this. So you can see at the first line, it's got foo.cpp. It will map to the object file. Then we have the IDL file. It maps to 4 files, and so on. So when HiMake reads build description files again, it will check against the new computed set of source files and derived objects against this index, and then delete all the files that aren't in the new set. Okay, building faster. You probably know recursive make considered harmful. That's a paper from Peter Miller in 1998. He thought the good thing was to have one really large makefile with all dependencies in them, a global view of all dependencies. And HiMake used to do that for a while, but that was okay for a full build, but we found out that we have just an incremental rebuild. That was rather slow, because Make spent so much time analyzing all the dependencies before it started rebuilding the few files that had actually changed. And I think it was because the DAG was too large and too complex. So instead, HiMake uses 2 levels of makefiles. There's one makefile per package, one top-level makefile that determines the order in which a package shall be built, and that gives rise to a shallow recursive make. So if you got this simple DAG there, you will end up with a makefile like this. And that, when it comes to parallelity, we can observe that package A2 and A3 can be built in parallel with each other. And when A2 and A3 are built, A1 can be built, and then finally X1 can be built. In HiMake, each package has 2 stages. There's a stage 1 that generates header files and CPP from IDL, for instance. Then it exports all these header files, and that is not done in parallel for some reason. That is kind of complicated to explain. And then we have the stage 2, which compiles CPP into object files, creates libraries, and creates executables. And then we made this observation that the stage 1, that is to compile IDL into header and CPP and copying, that is really fast. But compiling C++ into object file, that's slow. So HiMake will then transform the DAG so that more slow work can be done in parallel. So you have the same DAG like this. That's a package DAG. That will be transformed into this DAG. And here I was supposed to have some colors. They're not here. But you can probably see that there's some suffixes here, S1 and S2. But the thing here is that for each package, we can start the slow stage 2 as soon as the fast stage 1 is completed. So if you look here, okay, that one, stage 2 there, can be completed as soon as that one is completed. In addition, we can now compile all the C++ files in A1, A2, and A3 in parallel. Because you can see up on this level here, we got all the S2, stage 2 is here. So there are so many more files that can be built in parallel. However, doing this, even though it's a shallow recursive make, it requires 1 + 2 and make invocation. That can take a long time. So incremental rebuilds are not fast enough because it still takes a finite time to just invoke make. So what HiMake has got, well, okay, we could tell the user to do various tricks. We don't like to tell the user to do that. So again, TUP inspired a feature to do a minimum rebuild. So it's something we call an Xauto, exclude automatically. It prunes the DAG. So after a successful build of exe1, HiMake will create a database with the command line, the timestamp of every source file, and the DAG. And you can see the DAG here. But it's actually not that DAG that is recorded. It's this DAG. Did you see the arrows changing direction? So they're now pointing upwards. So when the build command is repeated, HiMake will now check against the database to find changed source files. So if you look at this package B2 there, has a lot of source files. One of them has changed. So, OK, it knows that B2 has changed. Then it just follows the arrows upwards. So it must rebuild A4 and A5, A2, and exe1. Then it makes the inverse list, the green ones, and then it just removes them from DAG. So instead of building all the packages, it just builds the few that must be rebuilt. So it will then generate a top-level makefile that looks more like this. You can see there are some yellow lines there. There are some conditionals in the makefile. So, and that is, the make will just skip a lot of things. It will not do the actual build. So in order to invoke with this automatic exclusion, it will set first a number of environment variables. All the packages that shall be excluded have this equal to true, and then invokes make on that. So this Xauto mode has two modes. The basic one, where HiMake will check each and every source file in this index in the database, and then find a set of change packages. And that is easy for the user, but sometimes that can be too slow when there are many, many source files. So in that case, the user can provide HiMake with a set of files to check. So you could query the version control system or query the IDE or whatever to produce that list. Then it will just check those files and update those files later on. Another thing that we do to build faster is to reduce the number of directories to search for include files. Our coding standard recommends that the CPP and the header file should be in the same directory. So unless we do something, we will actually end up with thousands of -i directives. And then the build will be slow, because for each and every hash include of something, there are so many directives that must be searched. We also found that some tools have this limit of no more than 1024-i directives. So HiMake does one thing. All the header files that shall be made available to other packages must be exported. And the default is to have one shared export directory for one package set. And assume, depending on how many packages there are in a package set, we might reduce that by 10. But that can still be too many -i directives. So we also optionally allow the user to specify that all header files shall be exported to one single directory. And we have seen really good build improvement times on that. Okay. Everything in HiMake is a package. And we can, and it's a DOG of packages, and then we can modify the build by changing the DOG. Just to do a small recap here, you have seen the standard package, which produces a library, or it can aggregate other packages. Then we have this program package that produces one or more programs or executables. And then there's a new package type for you, which we call a virtual package. It's an interface to precompiled libraries, but we can also use it to set compile flags or to check preconditions and things like that. And now that's what I'm going to talk about for the next few minutes. Okay, this is what the user has written in a HiMake file. So the point here is the keywords can add implicit dependencies, because the user has this, and the graph looks like this. And then the user says, I also need an IDL3 source file into this package. The green line there, green line. So that's what the user specifies. But associated with that keyword, there are some dependencies. So the DOG will then change into this automatically. So somewhere, someone with knowledge about this IDL compiler knows that it needs a dependency to B1, Z1, and D1. Then we have the platform. If you recall, the platform is something you specify to build for Red Hat or for Integrity or for Windows. That one, the platform can change the DOG. It can add include directories, link time dependencies, or some platform-specific packages. So the platform adds include directory. If you have a source file like this, and you do hash include or syssocket.h, when you're on Linux, and I suppose on Windows, you don't have to specify something like the blue -i directive there. The compiler just knows where to find the system headers. But if you are on other operating systems, it's not that easy. But the user shouldn't know that. And we don't want any operating system specific -i directives in the compiler configuration. So what we do is that the platform specifies a global dependency to a package that represents the OS include directory. So we have the DOG that the user knows about. Then the user specifies a platform MCP integrity 11. And that is an real-time operating system for our target computer. And then you can see within that platform, it has a file. And then it specifies a global dependency to this OS int 11/include. So each and every package will then get a dependency to that. If you look into that, the green package there, you can see it's a virtual package. And all it does, it's telling HiMake, there is some include files in this directory. And I want you to use this -i directive. Okay, and then we have some link time dependencies. It's kind of the same. We have this, this is a kind of a bit more complex DAG. So this exa1 depends on a C++ file and has A2 and A3 as dependencies. And when we build for Red Hat, that's probably what the DAG is going to look like. But if we're going to build for our missile computer, we specify another platform. That one, in that platform, there's a statement saying depend.hmk program. It means that these 3 dependencies there shall be applied to each and every executable in the system. So HiMake will then add these dependencies. Can you see the green lines there? No. Okay. There are green lines from the executables down here. There are no green lines from A1, A2, and A3. So it just, these dependencies are only added to the executables. And if you look into one of those new packages, again, we see it's a virtual package. And it says there is a library which provides the C runtime, which is needed for linking.
What does virtual mean? Does that just mean?
Kind of. I needed a term to specify that it's not a normal package which generates a library. So I just, there's a virtual package. There's also something called a bridge, which I'm not going into, but that one invokes another build system. So it's just a tag. Okay, and then we have the platform can specify what kind of operating system abstraction layer to use. So assume you have a C++ like this. You use our runtime libraries get time local, which we can assume is implemented differently on Windows and Linux and real-time computer. So we have this DAG here. MyFoo just sets up a dependency to the runtime library OS Abstraction Layer. That one has some implementation. And then it sets up a dependency to the RTL OS implementation and RTL OS interface, the ones at the bottom. But those packages don't exist. They are just hooks or placeholders. So when we build for Red Hat 7.2, inside that platform file, you will find some package substitution statements. It says to substitute It says to substitute RTL/OS implementation with RTL/OS Linux implementation. And the same for the interface. So when the build is actually done, HiMake will replace those 2 placeholders with the real implementation for that operating system. And if you're going to build for Windows instead, there will be a similar set of statements, keywords, But this time it replaces them with the implementation for Windows. So the graph will change into this. Okay, and then we do something to ensure build saneness or build consistency. Because in our division we have two major application frameworks. And some of the components, software components, only work with framework number 1. Others only work with framework number 2. But if you mix by mistake framework 1 and framework 2 components, you will get very confusing build errors. And instead of giving them build errors from GCC, we try to give them a more reasonable build error from HiMake. So we use, again, some virtual packages to check some build precondition. Those two packages there are more or less the same, but you can see one is for the framework 1, when we call it a checker, and it uses a conditional if not def RTL framework 1. And then if that one is not set, we will issue an error. And the other HiMake file is more or less the same. It just uses framework 2 instead of framework 1. So what we then do is all the framework 1 components or packages set up a dependency to the framework 1 checker. All the packages in the framework 2 set up a dependency to the framework 2 checker. And then if someone in package A1 sets up a dependency to one from the framework 1 and one from the framework 2 and tries to build where he has specified, I'm going to use framework 1. That will then issue this error. This component requires framework 2 architecture. I admit it could have been more precise. It could have said that framework 2A requires framework 2 architecture, but it's good enough. Okay, it seems I got time to do some esoteric features. Okay, we have license reporting in HiMake. Because, of course, we use some third-party components like, well, Boost. And they have some kind of license, BSD, Apache, MIT, or sometimes a commercial license. So when we build a product, how can we find out what licenses are actually part of this executable? So how we solve that is that a package that has some kind of license uses this keyword HMK license, and it just attaches the license text as a file. It could be a text file, it could be a PDF, or it could be an image, whatever. HiMake doesn't care. Then when HiMake traverses the DAG, it picks up all these entries, copies the license files to a directory specified by the user, and creates a report. And we do something similar to security classification, because since we are in defense, there are many, well, at least 3 security classifications involved. So what we start with is that each and every source file in our version control system has an explicit security classification as a comment, magic comment. So the challenge then is when we're building an unclassified product, how do we know that each and every source file is actually tagged unclassified? And nothing of a higher classification. Again, HiMake traverses the DAG, creates a report. So, and that, of course, requires that HiMake knows about this magic comment. Of course, when we have third-party components, they don't have this magic comment, so we have a whitelist in addition. So from the Boost, of course, doesn't have this comment, but we know Boost is okay. Okay, that led me to the conclusion. Having the package in the DAG is an enabler. It allows us to do so many things with the build. Changing packages, removing packages. We also found it's really easy to extend the build tool with new features. Like I mentioned initially that we had this Unity build support. To add that, I just changed one of the tasks to do that. And we also find that having central controlled configuration files simplify the build process improvement, because a build system is not static. It's not something you can say, I'm done. There's always a way to improve the build process. More parallelity, where to put the header files, fewer -i directives and things like that. But if that is distributed into hundreds of build description files, it's more or less impossible to improve the build process. Thank you.